Hello, this is section 4.3, and this is on logarithmic functions. So first of all, in the last couple sections we've been talking about exponential. The opposites of exponential are logarithmic, and what they mean by that is when you had something like like this, that was an exponential because one of the variables is in the exponent. That is going to be the same as log base a x equals y. So notice this, I said base a here, and I also said base a here. This exponent here went to that spot there, and then what was equal to goes in that spot there. So these are interchangeable. You can go from one side to the next. So for instance, if I gave you actual numbers in there, like let's say log base 2, 8 is going to equal 3. That's the same as 2 to the third equals 8. So again, these are interchangeable, or you can go from one to the next. That's going to help you in solving and evaluating them, especially if you don't have a calculator that changes bases. But if they said something like this, where it says log base 2, 32 equals I don't know, then the first thing that I would do is I would rewrite that as an exponential. So I take the log completely out and rewrite it as an exponential, and now I'm asking myself, 32 is 2 to the what power? So 32 itself is 2 to the fifth. And if the bases are the same, then the exponents should be the same. So x should equal 5. Okay? So that's kind of one of the things that we use those for, is that we interchange them like that in order to make it simpler on yourself. Okay. Now, some of the things that are going to make it easy for us are some of the properties of logs. Okay. So the first property that we have is if you have any base number here, but we have a 1 in that spot, it's going to be equal to 0. And the reason for that is because when we rewrite this, a to the 0, anything to the 0 power is always 1. So that's the reason why if you have a 1 in this spot right here, you're going to be equal to 0 no matter what. Then you have 2, the second one. If the base numbers are the same, if you notice that this is the same as this, then you're always going to be just equal to a 1. The third one, if you have these numbers the same but it's raised to some other power, then it's going to be equal to that. And the reason for that is because if you rewrite it, a to the x would equal a to the x. The equal sign's powerful. Okay, it needs to make sure that when you write an equal sign, it's got to be where it should be the same on both sides. And then the fourth property is if you have something raised to a log where it's got that base a, notice again, these two numbers are the same. It's going to be equal to whatever that x is. So when you see those types of problems, you can kind of go a little bit faster through that using those properties. So if you see something like this, where they take a 5 and a 5 here, as long as those numbers match, well, then it's going to be equal to whatever the exponent is, 8. Okay, so just so that you know, those are just kind of a ways to help you go along or help you go a little bit faster. The next topic that they're going to ask you to do is they're going to ask you to graph logs. Now, unfortunately, with your calculator for your TIs are always base 10. And the reason for that is because that's what we use when we count our numbers. We go by tens, okay, or we go by the tens places. That's part of our place value system. So our calculator is set up to be base 10. Well, how do you graph something that's got base 2? All right. So some of the things that you could do is you could rewrite it to make them look like that exponential in order to help you. But realistically, what's happening is if this was your exponential one from the last couple sections that we had, your log one is going to come in this way and ride out along the x-axis. What's happening here, you guys, is basically if I were to make that diagonal line go right through here, it's being flipped over that diagonal line. That line right there is that line of symmetry or reflection line is reflection about the origin, where basically the x's and y's are going to flip. So when we said for this one over here that the domain was all real numbers and the range was from 0 to infinity, if I just said the x's and y's are going to flip for this blue one, now the domain is going to be from 0 to infinity and the range is going to be all real numbers. Okay, so we're just making a flip. Alright, so everything's flipping from one to the next. Okay, when we said our asymptote was y equals 0, now this time our asymptote is going to be x equals 0. Okay, so everything about that is just going to flip over. That would be an example of, let's say, log base 5 to the x. Now what's going to happen in here as your number gets higher, they should cross through the same thing, by the way, too. That was just bad drawing on my part, but they always cross through that point right there at 1, 0. This would be something like log base 2 to the x. The higher in the number, the sharper the turn. So if I have something in here faster, that would be something like log base 7 to the x. Anything higher than that, it's going to be a sharper turn. The typical bases that you're going to see is base 2, 3, 5, and 10. Those are usually the ones that they use for those. But those, again, those are kind of your parent functions. Those are the ones that are going to be like that. Then from there, they might ask you to graph the same thing, but this time they're going to shift it around on you. So something like 2 plus log base 5 to the x. If you recall from chapter 2, a plus 2 on the outside means a shift up 2 units. So instead of going through this point here at 1, 0, it's actually going to cross, it's going to start turning there. So everything about this is going to stay the same, and it's going to come in here and ride out down that way. Your domain is from 0 to infinity because we did not shift anything to the left or to the right. Your range is going to be all real numbers because that's not being affected by anything, even if I just shift it up. And my asymptote is still x equals 0. Okay. Now the only time that actually changes is if we were to have something like x minus 3. Okay, now when it's inside parentheses, remember you shift it to the left or to the right. If it's a minus 3, we're going to go and shift everything to the right 3 units. So instead of crossing at 1, it's going to cross at 2, 3, 4. It's going to cross here. Instead of having the asymptote being here, it's going to be here. So we're going to just shift everything over. It's going to look the same, or as best we can. The domain this time, because we shifted it over 3 units, is going to be from 3 to infinity. The range is still going to be all real numbers. And the asymptote, again, because we shifted it over, is x equals 3. Pen makes it look like not equal to. Okay? So as far as graphing it goes, that's what you can about imagine, is that they will be giving you something like that. Again, if you're given base 10, you can put those in your calculator. That's not an issue. So if you see something like this that just says log and then x and there is no base number listed, there's no number down here, that's understood to be a base 10. Okay? So that's just kind of an unwritten rule. Kind of like if you just see a letter and there's no number in front of it, it's understood to be a 1. It's the same kind of concept. It's understood to be a 10. So you could actually put that in your calculator and that would actually work, no problem. The next type that you're going to see is you're going to see what happens when we have base e, which we had in section 2. We talked about the natural base number. The natural base number is then anytime you raise it to the e or have the base e, that's really the same thing as ln. ln stands for natural log or natural logarithm. All right. So when you see something like the ln of x equals y, that's the same thing, and remember how we rewrite it as e to the y equals x. Okay. So it's kind of that same principles that we had in the first couple examples where we were just interchanging things and rewriting things. Same thing where the properties of natural logs, the first one is if you have the ln of 1, which you could type in your calculator, you're going to get 0. And the second one is if you have the ln of e, you're going to get 1. The ln and the e are very similar to like adding to subtracting, multiplying to dividing. They're kind of like opposites of each other, where they're going to cancel each other out. So if you have anything where you have ln of e to the x, the ln and the e cancel each other out, and you're just left with whatever the x is. Or if you have it the other way, where e raised to the ln of x, they cancel each other out, and you're just going to get that x. So whenever you see problems like that, that's where it's going to ask you to basically, you're going to just be getting rid of one versus the other. So some of the problems that they have for you is something like this, where they're going to ask you to evaluate it, and I'll give you some of those problems. And I'm just kind of picking some out of the homework assignment. If they give you something like this, what I do is I set it equal to x, and now I have to then try to figure out what x is. So the first thing that I like to do is I like to look at the numbers themselves. I look at the base 6 and I look at the 36. And I ask myself, is there a way that I can make 36 look like 6 to the something? If there is, then I do that. So 36 is 6 squared. So if I go 6 squared, then remember those properties. If those two numbers are the same, then it equals whatever the exponent is. Okay? It's kind of one of those things where if you can use those properties, they're going to make your job go a lot faster for this. Again, I'm going to set that equal to x. Now, an alternative way of doing that same type of problem is if you rewrite this as an exponential, you're saying 9 to the x equals 81. Well, then what I do, again, is I look at, is there any way I can make 81 look like 9 to the something? 81 is the same as 9 squared. And if the bases are the same, then the exponent should be the same, so x should equal 2. So kind of two different ways of attacking the same problem, but they will give you the same result. That's when the x is there at the end. One of the things that they also do for you in problems is they change it around. So they might say something like the log base 2x equals 5. Again, rewrite this as an exponential. Okay, so if I do that, I have the base of 2 to the 5th equals x. Now it's just a matter of taking, if you know what 2 to the 5th is, or if you don't, take a calculator and type 2 caret 5 and see what you get, and you should get 32. Then the last one that they're going to see is what if they give you x in the base number, and they give you 25 here equals 2. Rewrite it as an exponential. X squared equals 25, and how do you get rid of square? You square root, and you should get x equals 5. Now, typically when you square root in an equation like that, you should get plus or minus, but remember, our bases cannot be negative. Okay? According to what we had in previous sections, where we were saying a is greater than 1 or a is between 0 and 1. They're not negative, so therefore, that's why we're not going to put the negative there. We're just going to put the 5. Okay. Then after that, they're going to ask you to evaluate, which means just plug it into your calculator and see what happens. And then some graphing ones, which again, we already kind of went through those already. So that's section 3. See ya.